Okay, hello and welcome everyone to Biotensegrity Party number 33, Math, Art, and Biology. The Biotensegrity Party is a production of the SM11 Biotensegrity Archive, whose mission is to offer education, increase awareness, and build community. And where am I here? I'm your host, Chris Marita Clancy, coming to you from the unceded territory of the Coast Salish Nation near Vancouver, BC. And I am here with co-host Graham Scarr from Nottingham, UK. Hi, Graham.
Hello, Chris. Hello, everybody.
And Susan Lowell de Solorzano from Washington, DC. Hi,
Hey.
Susan.
Hi, you got it, Chris.
I got it. I stumble over names. And today we're very excited to have two special guests, Daina Taimina from Ithaca, New York. Hi, Daina.
Hi.
And Margaret Wertheim, who's coming to us from LA. Hi, Margaret.
Hello.
This is a very exciting time because this is our first Biotensegrity party where we've welcomed in specialists, leaders in fields that aren't necessarily coming from within the biotensegrity community. And this intersection of art and math and biology is really exciting to me. It's a way that I've been able to learn some of the math, which to me is quite complicated. We like to begin with our sponsors. So Graham, could you please let us know a little bit more about our sponsors today?
Yes, thank you, Chris. The Biotensegrity Party is an all-volunteer production of the Stephen M. Levin Biotensegrity Archive and made possible through the generous support of our wonderful sponsors. Starting with Handspring Publishing in East Lothian, Scotland, we have a wide range of authors and books suitable for movement and manual therapy professionals. They're offering a generous discount coupon to all those on the Biotensegrity Archive mailing list and our Zoom participants. Handspring also produce a weekly newsletter entitled Springboard, which you can join from their website, that provides details of their weekly webinar series, Move to Learn, hosted by Elizabeth Larkham. We're also generously supported by Chris Clancy's educational organisation, Embodied Biotensegrity in Vancouver, and which provides an excellent resource for those of you looking to learn more about biotensegrity. Embodied Biotensegrity and Tensabiolat are offering a tensegrity workshop on the 5th of December. The Christian Castro Arenas and Andriana Gratterol Fuhrmeyer.
I'm going to stop you, Graham, because the registration's closed for that now.
Oh, okay. I'll leave that little bit out. Sorry about that, Chris.
That's okay.
So I'll move on. Moving on. The Biotensegrity Party is also sponsored by Artifact Pro of Madrid, Spain, where you can find wonderfully constructed anatomical tensegrity models. Artifact Pro also offers a generous discount coupon to our Zoom participants. And next we have the kind support of the Fascia Hub, previously known as the British Fascia Symposium, who are now organising a new platform called thefasciahub.com, which starts with a full day of talks on the fascial pelvis on Saturday, 28th of November. So register soon, thefasciahub.com. And finally, Integrated Biotensegrity, based in Alberta, Canada, are holding a one-day course tomorrow, Saturday the 7th November, with Lisa Babiuk, Paul Thornley, and Rachel Tudor. So check out all these events and offers and support our sponsors. Back to you, Chris.
Thank you, Graham. And I want to just say a warm welcome to all of our guests, our audiences here today, to remind you to please mute yourself. So that makes the quality of the audio a little bit better for our audience. To say hello also to those of you who are joining us on YouTube. We've got one of our team members, or sometimes more, monitoring the YouTube channel. So you can please let us know where you're from and put in any of your questions or comments there, and they will share them with us here on Zoom. Thanks to the Brazilians, who I know a lot of you popped on an hour early, not knowing about the time change. We're glad you stuck it out. And before I give official introductions to our guests, we like to have an opening toast. Margaret, where are you here? Everybody's shifting around on. Margaret, would you please do us the honor and thank you. Hi. I'd like to give an opening toast for us.
Thank you, Chris. Well, welcome everybody. Thank you for coming on this, what here in America is probably one of the most special days of the century. But I would like to give a toast to everybody in the Biotensegrity working groups and also to coral reefs, which I'll be talking about. Coral reefs, as I'm sure you all know, are on the verge of disappearing, and we need all to work on their behalf to save them so that they can do what they do for planet Earth. So to all the Biotensegrity people and to the future of coral reefs, welcome.
Cheers.
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 Thank you, Margaret. Thinking about the coral reefs and biotensegrity itself, we're always really focused on the continuities instead of just the divisions and the separations. So can't wait to see your presentation. But first, I would like to formally introduce our guest. Margaret Wertheim is an internationally noted science writer, artist, and curator whose work focuses on relations between science and the wider cultural landscape. Her work is animated by a twofold perspective: that science is a field of conceptual enchantment. Science is a field of conceptual enchantment and a socially embedded activity with political and communal consequences. Margaret is the author of 6 books, including The Pearly Gates of Cyberspace, Physics on the Fringe. And she has written for New York Times, The Guardian, Cabinet, Aeon, and many others. Margaret and her twin sister Christine are co-founders of the Institute for Figuring, a Los Angeles-based practice devoted to the aesthetic dimensions of science and mathematics. The Wertheim sisters have created exhibits for many venues, including Hayward Gallery in London, Science Gallery, and many more. Their Crochet Coral Reef project is a worldwide participatory science and art project, I think the biggest in the world. And it's been shown internationally at the 2019 Venice Biennial, Andy Warhol Museum, Museum of Arts and Design, the Deutsche Museum in Munich, the Smithsonian, which I'm sure is where you saw it, Susan, and elsewhere. Margaret has worked on all 7 continents and stood on the South Pole. Her work as a science communicator, she has won the annual award for the American Association of Physics Teachers and Australia's Scientia Medal. And we'll get some links to how to follow up on Margaret's work in the chat. And Daina Taimina is graduated summa cum laude from the University of Latvia in Riga, Latvia. Her PhD thesis advisor, I should have gotten, Daina, can you tell me his name, please? I should have gotten.
Rūsiņš Mārtiņš Freivalds.
Thank you. I'm not even going to try and repeat that. He was world-renowned for his work on theoretical computer science. Now, for 20 years, Daina taught different mathematics courses in the University of Latvia. And if you saw her TED Talks, which I had posted in our Facebook group, I love this story about really that shift that happened when you had to teach hyperbolics, which I hope you will share with us. She retired from teaching in 2015 in order to have more flexible time for her different projects, talks, exhibits. Daina has participated in art shows in the USA, Belgium, Latvia, Italy, Germany, UK, Finland. Daina has written several books in mathematics. And this book that I happen to have, Crocheting Adventures with Hyperbolic Planes, which in 2012 received the Euler Book Prize for Best Book About Mathematics for the General Audience. That's most of us here in the Biotensegrity community, the general audience. And she's also written, I have here your most recent book, 2020, Experiencing Geometry with David Henderson. And it's published as an open, there you have it. Thank you for holding that up. It's published as an open access book. And if one of our team can put that link up in the chat and maybe hop over, and if it can get into YouTube, that would be fantastic as well. Okay, so again, a real warm welcome to both of you. You're rock stars in my life, and when you responded to my email, I was so excited. So it's a real honor to be here with you. I want to say that we are a diverse community, the Biotensegrity community, and some people have very high levels of traditional academic education. Danielle Claude Martin, for example, is a physicist. We've got Leonid, who understands math like most of us don't. And then there are others, many others, who are grounded in practical experience. We have many, many body workers, movement professionals. There are surgeons, kind of, then the doctors and the surgeons have a foot in both worlds, many of them. And now, because I come from the background of being a yoga teacher for many years, I'm speaking for those of us who are really grounded in the practical experience. So when we start to discover biotensegrity, because we are people who really feel in our bodies, this is our first experience with the concept of biotensegrity, and it makes sense. And then we come across the concepts in the paradigm, which include math, and we get overwhelmed. And so your work, both of you, helps those who are, we call it math traumatized, and others who simply feel that understanding mathematics is beyond their reach. That has certainly been my experience. Even this morning, I woke up with a new, oh, maybe that's what that means. So Margaret talks about how to play mathematics and mathematics as a performance. Our colleague, Jaap, is an embryologist, Jaap van der Wal. He says, from the beginning, your body is a performance, a lifelong process. Daina, you speak about the importance of experiencing meaning in mathematics and in geometry. Experiencing meaning. I think this is something that's left out of most of our, certainly my age, our school education. So Daina, I wonder if we could begin with you. For hundreds of years, mathematicians believed that we couldn't make models of hyperbolic planes. Now, I'm going to leave it to you to explain what a hyperbolic plane is. And then those of us out here who watch your TED Talks, you had this breakthrough with crochet. Will you please share that with us and explain how experiencing geometry can help us explain complex math to non-math people?
Okay, well, thank you, Chris, and thank you and welcome everybody. And well, I have to correct you a little bit. So you said you started to read my book. I see you didn't get to the chapter 5. Where actually,
I didn't say I
where actually, yes, where actually I'm talking about, like, you know, like it's the models, you know, like the model of hyperbolic geometry was not needed until the end of 19th century, because it was needed only after the theory was made. And then they wanted to know on which surface that geometry will work. And therefore, the very first actually tactile model, which is in this book, and it is, so.
Oh yes, is this the paper model?
It is right here. It is right here.
Okay.
It is right here. And that was done, yeah, so that's a page 15.
Okay.
So, well, and that is and essentially, like what it is, it's like it was done by Beltrami in 1868. So, well, but then the mathematicians didn't like much of the models, you know, they were doing like this whole thing more sort of like on a paper and making a, so well, but what that model looked like, I can actually show you, because there is advantage to work from home. And there is a model which I never take outside. So that's the one which inspired me. And you can see you can see why I'm not taking it.
Mm-hmm.
And then this one is the same as Beltrami was done. Well,
Okay.
not the same, but the same idea. Yeah, so because like we can wrap this one around. And then this is a one which made me to crochet my very first model. And that's my very first model. So talking about the meaning is that the meaning is like the one of the meanings, and which is also comes from the 19th century going into this thing is like what is a straight line? And there is a book which belonged to David, so my husband, and here it is, like, and that was published by Kempe, and that is How to Draw a Straight Line.
Mm-hmm.
So the picture of this book is also in that in the my one. Well, so if we are on a piece of paper, and like our flat piece of paper, that is can be like our model of a plane Euclidean geometry.
Mm-hmm.
And if we want to have like a straight line, so then it's simple. So we just take a piece of paper, we can fold it in any place. And then when we open it up, so we have a perfect straight line. So, and that comes from the symmetry of the Euclidean plane, and then that is can be like infinite in all places. And we have like this, and then really like, so here we can experience in a very tactile way. In a very tactile way, we experience what the straight line is. If we are having, and I have to apologize, I forgot about like a ball.
I've got a ball.
Okay, well, anyways, no, it's okay.
Here. I have one here. There we go.
I have it.
Oh, you have one. Okay.
I have it. Yes. So we can talk like about, well, this poor thing is bigger than the ball, but so what will be the ball? So this ball, so this is an example of the constant positive curvature. And then essentially this is what we are having, like the differences between the geometry, because mathematical theory of geometry is just describing the surface. And then for a flat surface, that's where we are using Euclidean geometry. And now, like when we are having a ball, which was known already to Euclid, so that is where the spherical geometry works. And then, so that's where the spherical works. And so when Gauss was thinking at the beginning of 19th century about like a surfaces code to describe, so that is like an absolutely logical question. If we have a positive numbers, negative numbers, and zero, that same thing should happen with the surfaces. And that was there should be a surface with a negative curvature. And then that's where the question came, what is it? Well, and of course, then you can look in nature. And that's when I loved, when I first started to lecture also about this, like about these things, I was bringing with me sort of like a pictures of lettuce leaves, actual lettuce leaves. And then, we have a kale. And then another negative curvature is this wonderful angel trumpet, which was growing in my garden, but no more. So that's we are having like this connection, and we can do these observations. But still, and then one of the meanings we would like to experience is what is straight on these all different surfaces. Like we know about the great circles, which are like on a sphere. But then, I want to show you another picture from my book, which is here. And I was really impressed when I saw them in Met Museum in New York. I was just like absolutely stunned. These pebbles are late millennium, 7th millennium BC. And they are saying like so the sign said decorative pebbles, but I could see they are not decorative. So they are just like really somebody engraved. I wish I would know who and why, because it's really experiencing what is parallel, what is perpendicular. And it really comes, you know, like from so long time ago. Well, so for me, it was, I wanted to get like this curvature, like, you know, like this negative curvature. And what it is negative is that if I take a ball, I have to show you like with the fingers. If I go like this and I go like this, you can see that my fingers are in both, my fingers are pointing the same direction. I can put it like here also, and then they are again the same direction. For those who know differential geometry, those are like normal vectors going into the same direction. But this one, you can, so with the fingers, I can show to kids and they understand. If I go to the surface with a negative curvature, which actually is also on our bodies, and so well, but then I can show like it here. So you see there will be one finger will go this direction, and then the other one will go, so, okay, so essentially it goes like this. Yeah, so yeah, so that's what it is. So that will give us negative. But talking about that, I want to know what the meaning of straight is. So that is when I wanted to have, you know, like that I can fold it, like I could fold. So the same what I did with a paper, I wanted to fold it. Because one of the things is, if we are having and the thing which puzzled me was that if I'm having a point outside the line on a plane, I can have only one line, which is parallel to the given one. While in hyperbolic plane, I can have infinitely many. And that point of infinite, that's what was bothering me. And I needed something tactile. I needed to find this meaning. So like, and therefore, like, that's when I crocheted these things. And then that's when I can fold it. I can fold it. Yeah, and then I can fold another one. And then this picture is already here. Yeah, so you can see like I'm folding them. I fold it. And then I drop them. And then what happens is, then I really experience and kind of like I got this, okay, this is what is happening. Because in a hyperbolic plane, these lines are coming, there is only one place where they come close by. And then they are diverging to each of the directions. And then there is for each of them is only one place, and that place is moving. Like for the ones in the middle, that is this one, this common perpendicular, I can say. But then for this one, that will be somewhere here. Or for the other ones, you know, like there is somewhere, so that is somewhere here. And there is only one such thing. And that is something like, you know, like you really go through your fingers. And this is what you understand. And so it goes. And then it goes like explaining all the growth. And then what happens with crocheting is that we are getting like all these, like the number of crochet stitches is growing exponentially. And then this was one of the things which helped in some ways. The people who participated this year, I had an art project in Riga, and like an explaining how the virus, how the virus is growing exponentially, and you have to be very careful. And then you get like this little thing. This is what happens if you are adding a stitch to each stitch. So it goes like exponential curve is 2 to the x, which is very fast. And you see that this is not like too far away, you know, like that is like a tiny bit, and it's already things. And then what we can see is a connection between all three geometries actually, because nevertheless, this is hyperbolic plane, which looks like a sphere. So each hyperbolic plane can be enclosed in some sphere. And then when we are having like this transition from one geometry to the other one, so that means there is somewhere that 0 point, you know, like when we get like some tiny bit, you know, like a little piece. So it's very close to Euclidean geometry. So therefore, like these surface geometries, they they can look very different, describe very different, but when you zoom in, then they are all sort of like converge into the one.
So depending on what scale you're at,
Yes.
the geometry is going to be very different.
Mhm.
I know what my next crochet project is going to be.
Okay, yes.
And
Okay,
I
well, I
imagine,
was trying to get into my 10 minutes. I guess I went over, but that's
well, that's okay.
well, that's so
Yeah.
questions can be, yeah.
No, it's very exciting. I imagine with that one, you really feel the changes of force quickly, and it would become so tightly packed that you must get to a point where it's not.
Oh, yes, you can't really, yeah.
Can't really continue. Yeah. Okay, let me keep going. I'm going to move on now to Margaret. So Margaret, your project with your sister, Christine, the Crochet Coral Reef project, really it's reflecting this power of interconnection. It is by far the largest collaborative art project in the world. And so in the model of biotensegrity, we talk about heterarchy, how every part influences every other part in all directions, no matter how large or small. And so that what one person does really influences the whole. And you're finding this on many levels with the coral itself and with the people involved in this project. So I know you have a presentation ready for us. And as you present it, we're really excited to hear more about the Crochet Coral Reef project. And I'm also curious to know how participating in the project and how creating art has helped the people that you've been in contact learn about math and biology.
Well, thank you very much, Chris. I'll go to screen share. So as I have a presentation, so share screen.
Okay, we see your.
Okay, play from the start. Okay, so can you all see that screen?
Yes, it's gorgeous. I swim every day in the ocean, and when I started doing these crocheting, I'm seeing seaweeds and kelps, and the other day I saw a nudibranch, and it's like, oh, this is very exciting for me. Go ahead.
Okay, well, I'm going to try to stick to 10 minutes and just give you a very quick overview of the project as a totality, and then we can discuss more in the questions, etc., if people are interested in particular aspects. So the project that I do with my twin sister Christine Wertheim is that we are crocheting coral reefs. And so I just want to start by showing you some of the installations. We started this in 2005, and it was inspired in part by about Daina's amazing discovery that you could crochet of hyperbolic geometry. And my sister and I began to realize after a while that you could make these amazing mathematical models that like Daina was doing and use them for teaching non-Euclidean geometry in universities. But that if you deviated a bit from the mathematical formula, you could produce things that looked a bit wilder, in fact, a lot wilder. And that actually, once you deviated from the mathematical perfection, you began to create things that looked organic and natural, and particularly which looked like coral reefs. So in 2005, we began a project to crochet a coral reef. And part of the inspiration for us to do this was because my sister and I come from Australia. I hope you can hear my accent. And we grew up in the state of Queensland, which is where the Great Barrier Reef is. All Australians are very deeply aware that the Great Barrier Reef is the great natural structure that we are responsible for. And around 2005, when we started the project, was when scientists were becoming aware that corals were being devastated on a regular basis by this rising seawater temperature due to global warming. So my sister and I decided that we could do a project that would engage people with craft as we personally loved crafts, having grown up with it like Daina all through our lives, that we could engage people with crafts and also begin to try to educate the populace about climate change. Because in 2005, 2006, when we began the project, most people, particularly here in America, know about climate change. And it was really quite controversial whether it was happening or not. But coral reefs were themselves proof that this devastation of climate change was not something that was in the far future. It was right here and now. And coral reefs were being absolutely destroyed by it on a regular basis. That when we started the project, that nobody would have imagined the devastation, the fastness with which the devastation of reefs happened. Literally, the night that we started the project, Christine joked that if the Great Barrier Reef ever died out, that our woolly reefs would be something to remember it by. That was 15 years ago. This year now, several studies come out because the Great Barrier Reef has been utterly, has been hit extremely badly by several massive bleaching events in the last few years. Half of the Great Barrier Reef has now disappeared, and scientists are beginning to say that actually this whole thing, the largest living structure on Earth, literally disappear, not just by the end of this century, but in the next few decades. So we wanted the project to be an artistic response to climate change, a way of teaching people and introducing to mathematics, the wonderful mathematics of hyperbolic geometry and ultimately non-Euclidean geometries wider field. And we also wanted to do a collaborative project that we would invite in anyone who wanted to from around the world to participate in the project. And in this sense, what we're doing is emulating the way that actual coral reefs are made. So actual coral reefs are made by billions of tiny coral polyps, each of which is, about a few millimeters long. Individual coral polyps can do absolutely almost nothing on their own, but when they work collaboratively in their billions and their multitudes, they can create the barrier reef, which is a structure that is seen from outer space. So we wanted to emulate this collaborative, collective, working together notion of coral reefs to create artistic coral reefs that were collaborative and collective aesthetic enterprises. I've shown you a bunch of pictures of the generalness. One of the things that we've done is respond to some of the very specific environmental issues that reefs face, which I'm sure everybody knows by now, but they certainly didn't when we began the project. The major index the coral reefs are stressed and hurting and sick is they go white. So we've created a bleached reef, which actually is an audience favorite, even though it's an index of coral stress and ultimately showing the corals might be on their way to dying. We've also created what we call a toxic reef, which is a response to the fact that the oceans are being inundated, not only with carbon dioxide, but with plastic. So we have a whole of our project that's made out of plastics, which is our way of responding to this tsunami oceanic plastic trash, it typified by this thing called the Great Pacific Garbage Patch. So as I mentioned earlier, the project also grounded in mathematics. And here you see one of our small installations where each of the models in this particular installation are mathematically precise hyperbolics like the ones that Taimina makes. And we have moved them, as it were, out of mathematics class into the art gallery setting to show people just how much mathematics is underlying nature. And the idea that math is underlying nature rests at the heart of a lot of the work that I do, not just the Crochet Coral Reef, but I've been interested for 30 or 40 years throughout my career as a science communicator in the issues of how, in a sense, enchanted the world is, that mathematics throughout nature constitutes a kind of enchanted, magical dimension of the world. And about 20 years ago, I set up an organization. It's really my sister and I, personal practice, but it's called the Institute for Figuring. And our goal is to find ways to introduce audiences to mathematics, science, physics, computing by giving them activities where they get to play with ideas like crocheting mathematical surfaces our whole philosophy is that we want to give people access to ideas that are usually presented in math and science through symbolic means such as equations and textbooks. But we want to say you don't have to necessarily learn this through equations and textbooks. You can do it by things like crocheting, cutting and folding, weaving sticks together. So we set up this organization to do that. And part of the question that we're interested in is, what does it mean to know mathematics? Obviously, Daina and I both went to university and studied mathematics and got degrees in it, but that's not going to happen for most people. But we believe, Christine and I, that a lot of mathematics, not all of mathematics means, because there's a point where you have to go into symbols, but there are a lot of mathematical ideas that you can get into, at least conceptually, in a fairly deep way through playing. And raises the question, as I said, what does it mean to math? And we want to claim that knowing math isn't just something that happens symbolically, that you can know math through embodied forms of learning. And I want to show you some creatures that are embodying mathematical concepts. Like corals, there are plenty of other hyperbolic things in nature, like lettuces, cactuses, sea sponges. Here's a whole lot of hyperbolic corals. Nature, it turns out, has a wonderful taxonomy of hyperbolic wonders. These are nudibranchs, or sea slugs as they're commonly called. And they have these hyperbolic flanges that help them propel. And I want to make the claim, sea slug, like a lettuce leaf and a coral, in some sense knows hyperbolic geometry through realizing it in the fibers of its being. Of course, sea slug is going to be able to pass a university math exam at Cornell. But I don't think that that should be the index of understanding. And one of the things I love about Daina's work and her work with her husband, David Henderson, is that pioneers and champions of using embodied practices in teaching at university level to say, look, there's a whole lot of basic mathematical principles that we can explore hands. And Christine and I are all great believers in this concept. I'm just going to very quickly show you another way of describing the three geometries that include hyperbolic geometry. As Daina mentioned earlier, there are three different types of geometry: hyperbolic, spherical, and Euclidean. Euclidean is the one that we all learn in school. Spherical is what appears on the surface of the earth. And hyperbolic is this strange thing that appears in corals and lettuce leaves. Now, there's lots of different ways of understanding this, and Daina took us through the notion of parallel lines. But for beginners, a helpful way of thinking about it is the following. You can think of it in terms of curvature. What is the kind of curvature that a surface can have? If it's flat, like a piece of paper or a tabletop, it's clear it has no curvature. It's all just the same everywhere. If I look at the surface of a sphere, like a beach ball, it's curved, isn't it? Mathematicians characterize that as having positive curvature. So if we have something that has zero curvature and something that has positive curvature, can we have a thing that has negative curvature? It's an interesting question. Well, it turns out that you can. So in some sense, you can describe hyperbolic geometry by saying it's the geometric equivalent of negative numbers. Just as you have zero numbers, positive numbers, and negative numbers, so we can have zero, positive, and negative curvature. Lovely concept, but what does it mean? Come back to this question. What does this mean? Well, one way we can understand this is by considering the ways in which you can, as it were, what's called tessellate a surface with little polygons. So if we look at a flat plane, a Euclidean plane, I can fill it with little hexagons so that there's no space anywhere. We all know that from our bathroom floors. If I do something similar to make a model of a spherical surface, in this case, I have to take away some of the six-sided ones and replace them with five-sided ones. And so by literally taking away some space, I pull the surface in on itself and it wraps up and becomes an infinite flat thing. It becomes this finite curved thing. So if I want to make the opposite, if I want to create, instead of this positive curvature surface, rather than negative curvature surface, this time what I do is I take away some of the six-sided ones and replace them with seven-sided ones. So I'm literally adding surface. And what that does, I'm adding lines and adding sides to the different shapes, and therefore adding surface. And that is what creates a hyperbolic plane. And this model is due to Daina's son. Sorry, Dr. David Henderson's son, Keith Henderson. Now, these model, so that also is a model of hyperbolic geometry. You can make these models with paper, and it's a lovely experience, and I can send you a template if you're interested. But by far the best way to make models of this negative curvature surface is with crochet that Daina discovered. And essentially, when you do the crochet, just as we added in lines or added in more surface in the previous models, literally with the hyperbolic crochet, we're adding in stitches, which is adding in surface. And as Daina showed us, you can stitch lines onto these hyperbolic models and make woolly mathematical proofs. So this mathematics of this playful, tactile, handmade mathematics turns out to be tremendously for even formal mathematicians, a way of showing the tactile truth of propositions that when I learned this at university, we had to take, as it were, just as a conceptual truth. And it was pretty hard to wrap your mind around some of this. But seeing it carried out in a physical model that you can hold in your hands is an immensely powerful tool. And that's what makes Daina's work so vitally important. As I said earlier, if you take models and make them exactly mathematically perfect with crochet, you keep enacting a very simple algorithm. But if and you can make things, these are all mathematically perfect ones, but there's only so much variety you can get through that. The revolution of the Crochet Coral Reef was made by my sister Christine, who's an artist, that if you deviated and made more mathematically imperfect, imprecise, irregular forms, they began to look like living corals. And so we started to play with, as it were, aberration, deviation from mathematical perfection. And we invited the people who were contributing to the project to engage in this, as it were, deviant play with us. And gradually what came into being over time is a whole taxonomy of forms. It's like, just as life Earth begins with simple cells, and billions of years later, you wake up and you find you've got a whole taxonomy of animals from peacocks to giraffes. So with the Crochet Reef project, we've gradually, with our contributors, evolved a whole a whole woolly crochet tree of life. And that is the part of the project that I think has been really exciting, that in a very real way, this project emulates and enacts biological evolution, as well as being, in some sense, global participatory experiment in applied geometry. So I'll just leave it there, and we can take up various issues if people are interested further in the questions.
I'll just read to you some of the comments from the chats. One is from Cobalt, who writes, "Yes, please," in terms of sending the template. And Maggie Burrows says, "Discovering the magic of the 9 times tables was what first opened her heart to mathematics." She says she fell in love. And there's comments about being amazed by my school teachers hadn't bothered to point this out in class. I remember that too, Maggie. And Carol Davis, Maggie says, joyous. Carol Davis says, reminds me so of Keats. Truth is beauty, beauty, truth. That is all ye know and all ye need to know. And we have from Neil to Margaret, as you address some of the difficulties of language as an obstacle to understanding nature and natural forms. We have other terms such as irrational numbers, which are very off-putting. Is there any possibility that we could promote more accessible terms? Perhaps nature's numbers might be a good starting place. This is from Neil. Do you want to respond to that?
Sure. Irrational has negative connotations in English, but from a mathematical perspective, it's just a formal term. So rational numbers in mathematics are literally numbers which can be articulated through a ratio. So you say 3/4, so that's 3 in the ratio of 3 to 4. 3 nines, 3, that's in the ratio of 3 to 9, or 1 to 3. Irrational numbers are simply numbers which do not have, they cannot be formulated in terms of a whole number ratio. And the example that everybody knows, of course, is pi. Pi can be approximated by the fraction or the ratio 22/7, but there is no whole number ratio that captures the fullness of pi. So for mathematicians, irrationality doesn't have a negative connotation. And so what I would, sorry, my cat's having, I've let my cat out. For mathematicians, I would say that the issue here is not to abandon the word irrational, but to bring into mathematics education a much deeper sense of how we come to these terms and what these terms mean. And it's one of the things that I believe mathematics education needs to change, is that a lot of the basic questions in mathematics are the very basic questions, like what is a rational number? What does irrational mean? These are the things that mathematicians spend hundreds, sometimes thousands of years trying to understand. And it's those things that we should bring into this classroom, in my view.
Okay, thank you. And for Neil, Neil's often grappling with the use of, we take these scientific terms and bring them to the non-scientific community. And there is this jarring that sometimes happens. Like last week, I think it was, we were talking about decomposable from the mechanics to decomposable. To us in biology, it feels a bit of an affront. So we have a question from Carol, and who asks, how did radio evolve into rational? This is for either one of you, I suppose.
Sorry, something cut out. Can you say the question again?
Sorry. Carol Davis. Carol, do you want to ask yourself? Do you want to unmute and ask, or do you want me to ask you? Carol, are you there?
Yeah, I'm here. I said, how did ratio evolve into rational? And I can guess because rational, well, I don't even want to guess. How did ratio evolve into rational?
Who wants to take that one?
Dana, do you want to answer?
Well, so that is so what it means, rational, irrational, you can say, which is commensurable and incommensurable. So it goes back already to Pythagorean theorem. If you are having a right triangle with each leg is 1, so then there is no finite ratio you can put hypotenuse in it. That's a square root of 2. So well, and that's how it connects. That's from where it comes. So that's like a long history.
Yeah, I mean, sorry.
I don't. Is it so? Did it give you like for me, like that's like that's what you can put like in a measuring. Can you put it like in a finite times the unit in the same same units? And irrational will be you don't.
So Margaret,
what Dana's saying is that the word irrational actually had meaning first in mathematics. This is one of those words where we get the concept irrational from mathematics. So it was a term that was literally used, as Dana just described, to explain how you could have a number that you couldn't finitely measure. And so originally it was a term that mathematicians used, and it has come to mean irrational in the wider sense that we use it in English now. That when you say something is irrational, it's not reasonable. But in mathematics, it effectively meant that it wasn't measurable, wasn't reducible to a finite, a whole number fraction. And it was late, and because that was in Pythagorean times, and that was actually regarded as something that was nearly mad. So the Pythagoreans were very troubled by this discovery that there were numbers like the square root of 2 that could not be reduced to a simple whole number ratio. For them, they actually did feel that such things, that the existence of that was the existence of something unreasonable and actually abhorrent in the world, and they tried to suppress the finding. So, and then it later became more used in natural language, this term of irrational. So there's always been this connotation of madness to it.
Well, there is a thing like up to discovery of this not being able to measure, because up to that, the Greek algebra was essentially, it was geometric, it was a geometry, everything was geometrical, and it was enough having rational numbers. In some ways, like these irrational numbers is enlarging the field of numbers, just adding another meaning, like what happens if we can't do something, so we add something. So yeah, and then eventually like meaning of a number expanded, and there were like a more and more. So may I show something while we are not too far from what Margaret described about like these stylings? There is like, I didn't had it on my way because like I'm glad that you showed about like a tilings, like that thing. But there is something which I usually use like when I have my only crocheting audiences of something. So like show like these positive, negative curvatures. That is like a very popular, at once was like, it's called African flower. And if you have like a 6-sided, like, so this is when we can do the tilings, like this is, if you like missed it and made it only one, so like that's when we are having a positive curvature. This is like a pentagon. And if we added the other one, like there's a 7, so this is already negative. And then what you have, it's like having a hyperbolic plane. So this is when you can crochet it. So yes, and then that's this one, like it's like a crochet version of that. And talking about like various models, also you have a link to that Experiencing Geometry, which is an Project Euclid open source. In appendix, there are all different models you can make, including these ones with hexagons and heptagons. And there is also like this way of a model, which you can do with triangles. And
Okay,
then so also, yeah, so yes, if you just go like online, and that's all that.
So there you go, Cobalt, the link for the Experiencing Geometry book, and it's an open source book.
It's an open source book, yes.
It's up
you
near
can
the
go
top of this chat, and maybe Rachel will put it in our newsletter next week. But one of the things that strikes me with both the crocheting itself, with seeing the work that you're both doing, is the beauty of this and the importance of the aesthetics of it. And you both write about mathematicians having this resonance with an aesthetic experience. And also, of course, for me, being a kinesthetic learner, the process, the performance of crocheting, like the performance of living or developing, evolving, teaches us something that is almost, it's Van der Waal calls unponderable. So this difference between science and like this original math, at first the irrational was maybe didn't make sense, unponderable. And now what we can understand seems, maybe what some of you can understand, seems to be expanding. So I wonder if you can speak to that. Margaret, I was listening to your interview with Krista Tippett yesterday, and this, and I would put that to you, the difference between the, the analytical, the go to school and learn, and the performance or the play of mathematics or physics even. Could you speak to that? I'm curious to know more.
Well, I think I agree with you that I believe we need to have a lot more of a performative dimension in the teaching of mathematics and physics, and various other scientific subjects, but those two are the most paradigmatic. And I think one way to think is we teach math now largely through symbolic means, and that's what professional mathematicians use, symbols. And we need professional mathematicians to be using symbols to give us the amazing math that they give us, which underlies everything from the internet to microchips. But for most people are not going to become professional mathematicians. Most people are never going to study math at college even. So most people need to be given access to math in a way that is accessible, and I would argue in a way that's a great deal more pleasurable than it currently is. For math is regarded as an absolute horror and chore, which is a shame because mathematics is deeply beautiful. And as I said earlier, a lot of math ideas that can be engaged with through material play, what Chrissy and I like to call material play practices. But this is not just an idea that comes out of the blue. If you think about it, where we get math from, we didn't just dream it up in our minds. Mathematics derives observations and interactions with the world. Mm-hmm. So, for instance, I go 1 sheep, 2 sheep, 3 sheep, 4 sheep. And one of the impetuses for counting was knowing how much stuff you had, whether it was sheep or later on gold coins and money. The big impetus for geometry starting was measuring of land in the Nile Delta. Every year the Nile would flood and people's property boundary erased. So they needed a way of measuring and laying out where's my land versus your land. And they're two very easy examples, but a huge amount of mathematics that we get, at least up until about 150 years ago, we got from our interactions and looking at the world and seeing, oh, nature does things that, behave in this way. And I can, as it were, apply numbers to that in some particular fashion. So nature actually is our guide here. Nature performs mathematical structures. We have the heavens, the stars, which in some sense are around the earth, or are we circling around them? But the whole notion of exploring three-dimensional geometry a huge part comes from a desire to understand what we see when we look out at the nightly sky. So much mathematics has come to us historically from our interactions through nature. So as it were, this idea that mathematics has to be purely objectified is in fact a modern abstractification, which only dates to about 150 years ago. So I'd like to bring us back to where we started with math, which is looking at the world around us, seeing how nature itself mathematical feats and saying, let's do similar feats with our own hands, with our own bodies.
Mm-hmm. I totally agree. Daina, do you want to speak to that before I invite Susan on, who I know has a question for you? Susan, are you there? Yes, you are.
Well, so that are like an example I want, just to understanding sometimes like a mathematical concepts. There was an example for me how I returned back to connected computer science, and then it was just like through these like these various stylings, kind of just like continuing like this embodiment. So this is now like making a hyperbolic quilt in a way, which seems amazing. Things are that they are right angle pentagons. So they are right angle pentagons, and then you can see like they are right angles. That's yeah. So well, and then apparently it's like there is another difference, like how you can think about like a meaning in these geometries that we all know about like a square grid. If anybody has a trouble with the seeings, and that is like, well, here it is, like a square grid, like which is an Amsler chart. But we can make it like these the squares will cover the plane, and we can make these squares larger and smaller. And then, and they were just like in various sizes and something. So, well, if we go on a hyperbolic plane, it's interesting that you can't have a square. So it is four angle, like 4 right angles. The pentagons are the smallest ones which you can have. And and this is the smallest grid. And then they are fixed on each of those planes. Yeah. So see, through different things, we can have like a different experience. And then there are like, I can show like later, if you want like examples, you can have on a hyperbolic plane, you can have a right angle hexagon. Here we go. Here are the right angle hexagons.
Mm-hmm.
And again, so so yes, and then we can have a heptagons, but they will be all, you can't like just blow them up like you can do it on a plane. So yeah, so and that is sort of like this tactile experience through meaning, which
for me,
yeah,
I see that, and it's just like I have to have it in my hand to really understand it. Even seeing it on video, I think it's different than if I have it in my hands, just because that is the type of learner I am. So I guess I have to make one.
So this is the first I made it like, I made it by stitching these, like really, this was my exploration, how it's possible to have these right angle pentagons.
Yeah. Okay. Now, see, that helps for me to see the process that you went through to create that. That helps a lot.
Yeah.
Yeah, that helps a lot for me. I hope other people are finding the same. Just a moment, I'm going to ask Susan. I know she has a question and a comment for you. Mm-hmm. But first, we welcome members of our audience to turn on their cameras if they wish. During this next part of our session, we like to have more of a community feel. So we invite members to turn their cameras on, and then it feels more like a party. And this is, after all, the Biotensegrity party. So Susan, please.
Yeah, thanks. And I really think at some point we're going to want to hear maybe from Steve on this, because he's done a lot of work with this idea of the 4-sided and the 5-sided and the 6-sided and working with quasi crystals and stuff like that as well. But anyway, my question, and I think you've almost pretty much both addressed this already. I confess we were having some technical problems with people not being able to get into the meeting, which I hope have been resolved. So I was a little distracted at some points, but I do some work with kids and adults too, who are having trouble with math, and because of the way it's taught traditionally in schools. And my goal is not just to help them get their homework done, but is to make them like fall in love with math. Because if you love something, you will learn more and more about it just naturally, and for them to feel the natural connections. Now, at the same time, I've done a lot of artistic stuff in my life. And so it drives me nuts because I hear people saying, I'm not artistic, or I'm not a math person. And so my question has to do with, how do we get people to understand we're all math people, we're all art people. The mathematicians are artists, the artists are mathematicians. The artists don't know the symmetries they're working with, for example. Anyway, so I'll just throw that out. Thanks.
Well, I think, sorry, I'm not muted. I think many people have the idea that they are not math people. It's one of the things we get told so much by people who participate in the Crochet Coral Reef project, that, and I should say most of the people who participate in our project are women. And I begin all of the workshops that I give on the subject in art gallery settings, or science museum settings, but many art gallery settings is where I have these workshops. And we always begin with a 20-minute discussion about the geometry underlying these forms that they're about to make. And so we go through the basic math that Daina took us through, and through this idea of how the different surfaces have parallel lines behaving in different ways, etc. And one of the things that we hear most often from our participants is how empowering these people feel it is to be shown that they can understand mathematics. And so in the context of learning to crochet and, aiming to get these people to participate in making hyperbolic corals, they learn about the foundations of non-Euclidean geometry. And throughout the workshop, we'll then have discussions more about the mathematics. And we end up discussing the structure of the universe, the structure of space-time, because it is this non-Euclidean geometry that Einstein used to articulate his general theory of relativity, which is a theory that tells us about the structure of the universe. So one of the things that this project demonstrates is that you can get people talking, general relativity and the structure of the universe by beginning with crochet. And people at no point are left behind or lost. I mean, if we can spend a little bit more time on a concept if people need to. But the point here is that there is no such thing as a person who is not mathematical. The human mind is innately good at mathematics. And I believe the reason for that is simple, that the human mind is innately good at learning languages. If we all grew up in China, we'd be speaking Chinese. If we all grew up in Iran, we'd be speaking Persian. We as humans are innately good at languages and absorb languages. Mathematics is the language of beauty and of structure and form. Mathematics is a formal language. The human mind is innately good at it. The tragedy and the problem is, how does it get beaten out of us? Somehow in our educational system, we beat out of people what is an naturally innate quality that all human minds have, I believe. And I'd say the same thing happens with art. Many people think they're not good at art. Well, that's only because, again, they haven't been given the opportunity in which to flourish in a project which enables them to do it in a way that's suitable for them. And it is something our society has really messed up on, that two of the great activities of the human, of culture, mathematics and art, were denied 99 to 99% of the people.
There's a saying among educators, if you go into a kindergarten classroom and you say, who can sing? Everybody puts their hand up. Who can draw? Who can do math? Who can do science? If you go into a 5th grade classroom and you say, who can sing? 3 kids put their hands up. Who can draw? 4 kids. What happened? How did everyone forget? So Daina, I know you were not an artist, right?
Yeah, no, I wasn't. No, I wasn't. No.
Someone tried to tell you were not an artist.
Yeah, no, I wasn't an artist, but I want to address like that what you were asking about, that some children with learning difficulties, because I had worked with them and sometimes making these big projects. So when I have been doing my installations, like it's not going to, so I really appreciate Margaret and Christine going like with making a coral and going like that. For me, it has been this crocheting together and talking what are we doing and exactly what happens and this human interaction. And I had like a experience when we were crocheting, like I was showing how to cut plastic bags before they were banned. And so, it was in Latvia, and I was working with a youth which were had like a learning disabilities, and they were like in this daycare. And usually they were being dropped at the daycare, and the teacher said, oh, it's so good to do with them something else, because all they were doing is 8 hours making like these linen sacks, like you just like a linen sacks, and then they were taken somewhere in and put some pictures on. But I think like it would drive anybody crazy that all day you are doing these gray sacks, like that's it. And then they were excited about doing these colorful plastics, and they were asking, what is it? And I was telling like them very simple. And then they started to ask after they did it. So, and they were working for a while, and then we put like so that was included in Latvian Reef exhibit. And the group of these youths, they came and they said, well, we want to know more about mathematics. What else you can show us? And then I was showing them that you can have something like a much more, like the things, because for example, you can have a regular octagon, which has 45-degree angles. And then this is the octagon, which is a very significant in topology. And you can put these things together. So you can sort of make these things together. And now we said okay, now imagine that then in the middle, so you can just put these 2 points together too. And then this is, which topologists are calling hyperbolic pair of pans. And now you can imagine that you are having these 4 holes, and you can put this hole here, and then you can put this hole here. And because I can't do it, but we need another dimension. And we went with these kids easy to another dimension. And they say and now you are having a pretzel. You are having what's, you can imagine how it is. So well, and then I was mentioning you, I said, fine, but we can do the same thing with something else. And what it is, we have these, we have four rectangular hexagons. And now I can put these hexagons together. I can put them together here in the middle. And now you can use your imagination, adding this hole here, and then this hole here. And that would be again, that's in a 4th dimension. And then what do you get? So that's when you are getting this torus. So yes, and then that's what it's interesting about hyperbolic geometry, because for a exam, I don't know how well I did it. So for Euclidean geometry, you can imagine that you can make this with 1 hole. For spherical geometry, you won't have any hole. But for hyperbolic geometry, here it is, you can have 2, 3, 4, and how many holes do you want? And then we can make everything that with a crochet. So here are some examples, and that is the plasticity of that hyperbolic plane. And here it is with the 3 holes. So yes, and that's done these various things, and that's what you can do with them. But I think that gets too far. So yeah.
Okay, thank you. I'm going to jump in here because I'm looking at the time, and Margaret, I know you have a very clear deadline when you have to move on. We do have a couple more questions, but before I invite the questions from the audience, I know that you are colleagues, you are familiar with each other, yet you probably don't get to see each other very often. Do you have a question for each other? Daina, do you have a question for Margaret? Margaret, do you have a question or comment for Daina before you leave?
Well, I know that I was luckier to participate in Riga Biennale this year, and when Margaret was supposed to be this year in Helsinki Biennale, but then that one got postponed. So I hope that we do meet with Margaret next year in Helsinki, because so I'm just I have this invited talk, and then I hope that Margaret's project will be with a coral reef there. So.
And what is that event, please?
Okay, so can you explain, so what is that event, Margaret? So tell about Helsinki Biennale.
Yes, so Daina has a wonderful project in the Riga Biennial, which is happening right now.
Well, it's over.
Oh, it's over. Oh, okay.
There is, I think, a picture of that in the newsletter.
And so she did a large community art project, getting people all over Latvia to crochet hyperbolic planes, and they put them together into this beautiful, beautiful imprint. Christine and I are participating in the Helsinki Biennale, which was also supposed to have been on this summer, but got delayed, obviously, because of COVID. What we're doing there is we're working with all the people of Helsinki to be crocheting a coral reef of their own, and we work with them to create a couple of new coral reef sculptures that are specifically made out of plastic and videotape. but it's one of the things that we found is that the people of Northern Europe, particularly the women of Northern Europe, amazingly good crafters. It seems that in the Baltic regions, and also we found in Germany and Denmark, so all of the Scandinavian, German, Latvian region, there seems to be a very, very high level of skill that women grow up with. And I wanted to ask, it seems to be still the case that women there are growing up learning to do crochet and knitting. Is that so? That young women
it used to be, yes, it used to be case that it's in a school curriculum. So you are getting like these skills, yes, up to now when they are saying, oh no, we need to change curriculums to be like more modern. And then, but it's first of all, it's fashionable that you make things and then you can make yourself unique things. But then the other thing is, it comes actually from Finland, where they were teaching like all kids and first graders already to knit and crochet. And so there were, I can't give like a reference immediately, but that's what they said, that if you are developing like those skills, that will help with math. And how it helps with math, not only by that you have to follow the pattern, but it also helps with that in order to get like some really aesthetically agreeable and nicely looking thing, you have to practice that craft and you have to work and you have to take it apart and then you see how you are improving. And exactly that is a feeling which helps, when you need to go to do math and other sciences and further, because, like in sports, everybody agrees you have to have like some, trainings. You can't just go and, perform world-class ice skating. You need to have years of training. But that happens anywhere, like you can't just jump in. You have to, you have to build up on your skills. And then for the kids, the easiest way is really to do various crafts, and not a fake craft, but when you are making something, when you are making a thing you want to wear, so so then you want it to be nice and nicely done, and that's so yes, that's a tradition, and it still holds, but unfortunately not as strong. Like for Austria, I know like they were doing postcards. Unfortunately, they didn't send me like how that project ended, but they were doing like a postcard, sort of like a social movement, not to cross craft out of curriculum. And then they were going to give them into various ministries and, like politicians and everything. Yeah, so because it's important, like a tactile skills.
Can you tell me, I'm so sorry, the event in Helsinki, I'm missing the name of it. Biennale?
It's called the Helsinki Biennial.
Oh, biennial.
Biennial. So there's the word, some people use the word biennial and some people use the word biennale. So in Venice, where we participated last year, it's called biennale. In Helsinki, they call it the biennial. In Riga, I think it's all biennial. Say in Sydney, they use so different people use it's like tomato.
Yeah, my American ignorance.
So
Thank you for clarifying that.
Riga, they also are using biennial.
Oh, we can't hear you because your voice, you have to move the so we can hear you. Your mouth is covered. That's better.
Yeah.
So there is our newsletter under the picture, actually the picture that's on that poster, there is a photo credit that says where it's from, I believe. Yeah, Rachel? Mm-hmm. Rachel, I don't see you.
If anyone wants to find out, you can just Google Riga Biennale or Helsinki Biennale, biennial, sorry, and you will get it.
Thank you.
Margaret, this you used, I wrote it down. Mathematics is the language of structure and form. To me, that's such a powerful phrase, and something that in the Biotensegrity community, we are thinking a lot about structure and form. And maybe Graham, if you wish, Graham talks about how in Biotensegrity, it's really bringing it back to first principles of close packing, geodesics, and minimum efficiency. So here's where we kind of bring the math and the science together. So this phrase, mathematics is the language of structure and form, really brought up to me how integrating what we've talked about today with biotensegrity. And I know you've just got like 7 minutes. You need to leave before the half hour, Margaret?
No, that'll be fine.
Okay, so Graham, you're unmuted. Did you want to speak to that?
Just to put a little plug in to say that I had a chapter on partly hyperbolic geometry in my book, Biotensegrity, the Structural Basis of Life. So there's another resource to go and feed a bit more, but I didn't know about crochet hyperbolics at that time. So this is just wonderful from what Daina and Margaret have presented.
So the next edition.
Yeah, and Steve, can you speak to this whole 4 or 5, I know you had stuff where people were telling you things couldn't meet the way you thought they could meet, and then the mathematicians or the physicist figured it out.
Well, it has to do with the whole concept of liquid crystals and things that you couldn't get a five-sided five-sided crystal. And of course you can get it with liquid crystals because you get hyperbolic shapes. But aside from that, what we're really talking about in biology, of course, is that these hyperbolic shapes also have to have physical structure that's going to be stable. So you need to combine the concept of these hyperbolic shapes with physical structures that are stable. And the picture behind me shows that. And here's one of the models. And this, of course, is hyperbolic and with so-called irrational numbers. And what we're doing is tensegrity is the structure that can do that, that can represent hyperbolic shapes and space in a structurally stable form. I think that sort of covers that quickly.
Yeah, so that was interesting. Interesting shape, but you are going. There is something, yes, which is holding it diagonally. You were watching it, and yeah. So okay. Mm-hmm.
I mean, we have these are these are
yes
really hyperbolic shapes that we're into here, and you can see the whole wall full of them behind me. That when you connect them, they're if you start adding, these are made with 3 tensegrity icosahedrons, but when you start dividing it up, you're talking about a whole combination of permutations of them. So it's not 3, there are many of them in here. And then these little ones are lesser ones than that, also building up to this hyperbolic shape. So here's a structural thing that is structurally stable, which you can't do with hyperbolic shapes if you, at least we can't in the gravity world, as far as we know, unless you got some sort of stability within it.
Yeah, so I agree, because I can show you the other shape. So this is an origami shape, and then you can see like it's really pulling it apart because it doesn't have that stability what you were talking about.
Daina, where does that hyperbolic origami come from?
That was my question.
Was that by Tom Hull? Was that by Tom Hull?
It was by, I think it was given to me. It was given us as a yeah. So see, it's just coming apart. I need to put it together.
Right.
Yeah. So and then the other one is, this one is a little bit better. Another hyperbolic shape, which is done by Curvahedra. That is like by Edmund Harris. So this is by his Curvahedras. So I think this is more closer, like to some kind of a except it's not like a straight lines, but it's like with these. So yeah, so all these shapes, but it's also not totally stable. There is some stability needed in there.
And who did that, Dana?
Edmund Harris.
That's fantastic. I've
it's called curvahedra.
Curvahedra. That's really beautiful.
Yeah, and you can do like a spheres, and you can do like that. Yeah, so no, these ones are, so this is okay, here we go. They can just start coming apart.
And does it, can you get them with, like, that one's some of those were sided and some of them were 5-sided, is that right?
Yes, yeah. Well, they are like, some of them, these are 4-sided. Yeah, so they are various. Yeah, so he has like various. So these are the 4-sided, and then this one is and then this one is 5.
That's beautiful. Wow, that's fantastic. Yeah. Really fantastic. Can I show you all something before I go? Because this, I think, might be of interest to you Biotensegrity people.
Do please. And while you're sharing your screen, you need to share your screen. I'll just pull this book up. This is from Henry Searman's book, and he's got 3D printed hyperbolic models.
Okay.
Can you share?
Yeah. What I want, can you see my screen now?
We can. We don't see the full picture though. If you press the play, I think.
Yeah. What I want to do is full. No, it's not full. Is it full now?
No, we see the main picture and it's bigger, and we see the thumbnails on the left side.
I don't want to.
Oh, there you go, to your far left.
Okay, so what I want to show you is that all. Okay. So it turns out that that carbon can make all 3 geometries. So in carbon atoms, which have tetrahedral structure, but it turns out that carbon can arrange itself in ways that mirror each of these 3 geometries. So carbon can be arranged carbon atoms can be arranged hexagonal shapes, which is what we call graphene. And graphene is these thin sheets of carbon arranged in hexagonal lattices like this, and it can be rolled into tubes, and it's now considered this huge wonder material. And Andre Geim, who discovered it, won the Nobel Prize for that discovery a few years ago. But carbon can also be arranged, we now know, into, as I showed you earlier, those models of a sphere, so that the carbon molecules can also, have the tessellation structure of 6-sided hexagons with 5-sided pentagons. And that's a whole new form of chemistry that is now called fullerenes, and it's named after Buckminster Fuller. The full name is Buckminster fullerenes. And so that was a discovery, one of the early 1990s. And that's also a whole new field of chemistry. And it's amazing what these fullerene molecules can do. And then 15 years ago, or maybe even only 10 years ago, it was discovered by some scientists in Australia that it would also arrange itself into the hyperbolic model, which I showed you would have hexagons and heptagons, 7-sided ones. And this is a new material that's now called carbon nanofoam. And people don't yet know what might use it for, but it's got amazing sort of heat properties, apparently. So it's a very, very interesting thing that it turns out that there is, on the atomic molecular level, realizations of these 3 geometries, which shows you again that although mathematicians spent hundreds of years trying to prove that hyperbolic surfaces were impossible, nature knows how to do it. And nature has this ability to constantly exceed our expectations. And So it raises the question, which I really like to come back to, is mathematics invented or discovered? You know, in some sense, we're rediscovering things that happen in nature. And I really like this notion again, that nature is able to embody these things that we ourselves think are impossible and that turn out to be not only possible, but out there in the world.
That's mind-blowing. I had no idea about this carbon nanofoam. But Steve, do you want to respond to that? Thank you for taking the time to share that with us, because I think a lot of us are probably very excited about that. Steve, are you there?
I'm here. I'm trying to find the thing I just put up on my screen, showing that we show this all the time as the oscillating icosahedron is really the nanofoam. Shared screen. Let me see if I can show you just one of it. Share. I mean, that's what we're talking about right there, is that it doesn't quite fit, so it's oscillating. So you have all these hyperbolic shapes recreating these forces that we talk about all the time, the oscillating bubbles and foams in tensegrity. So we're right with you.
And the foams have to do with all the soft matter stuff as well.
Oh yeah.
Everything interlinks with everything else. And you've been talking about the fullerenes for years too, Steve.
Yes. That's so. I mean, I started with the fullerenes actually.
So interesting. Wonderful how it comes together.
It's super exciting. And I know that Wilbur has a question and Patricia has a question as well.
And Andrew has a question too.
I'm unfortunately going to have to go.
Yeah. So,
but thank you very much. It's been a wonderful discussion. It's so lovely to be here with Daina. And I hope, Daina, that we will get to see each other next year in Helsinki. Lots of love and congratulations on the amazing mission in Riga. It's really beautiful.
Yeah, okay, so well,
thank you.
Wishing you luck, and then I'm looking forward to seeing in Helsinki.
Thank you. And thank you for inviting me to be a part of this, Chris.
thank you so much for being here. It's very exciting to hear everything you have to say and see and share. And I know there are probably lots more questions, but we'll speak about them with each other. So thank you. Good luck with the cats and with your next endeavor.
Thank you. Thanks to all.
Thanks for coming. Such an honor to have you. Okay, so
Chris, I was just saying, Andrew also has a question I want to make sure you get to.
Oh, okay. I did not get hit. So I'm going to just, Patricia's been waiting. And are you able to unmute, Patricia, and ask your question?
Okay, so Daina, I had a question about straight lines, kind of scanning through the chat to see if I can find what I wrote. Okay, so I have heard it said that there are no straight lines in nature. And the latest place where I heard this said that it's, even if you thought there were before, as we're able to enhance what we see in nature with microscopes at higher and higher levels, that it becomes even more clear that there are no straight lines in nature. So my question for you
disagree.
is,
totally
yeah,
disagree.
so my first question was, is that true? And then I'm interested in any comments you have about that idea and how it relates to Euclidean geometry and its continued relevance.
Well, this morning I went to, fortunately, the picture is on my cell phone. And so, well, we have a beautiful park near here, which is like a Upper Tremont Park, and I absolutely love it. I'll try to show you. And I was taking a picture actually where there are, yeah, I don't think that it will be particularly clear seeing so well, but anyways, this is okay. So these, I don't know how well you can see, but these are like straight lines making an angle. So what is a straight line? Straight line is an abstraction. and since Plato's times, there is no point, like there is a point and line and circles, they will be always ideals. And those are ideals which Plato has already said. These are ideals which we make like this perfect form in our head. So of course nothing is perfect, like, and if you're going, but then those abstract forms, like in mathematics, those are the ones which is used to describe what is happening in nature. And then of course, like, you are not going to have anything ideal, like and like a straight line. But otherwise, no, absolutely, I totally disagree that there are no straight lines. I can show you, like, today I was like exactly thinking about, like, I need to take a pictures because they are having such a perfect straight lines there on a cliffs which are made like after Ice Age, when there were like a river going through and cutting through like this limestone and whatever those shells, and they are just like so beautifully straight. Yeah, so well, yeah, no, it's
Thank you for that explanation, actually, and the question, because it brought an explanation that really hits home. Patricia, do you want to say anything? I see you have to leave as well. Patricia,
no, I just want to confirm that I understand. So what I hear you saying is that the straight line is a perfected version of an abstract form, and that it doesn't exist in nature in that perfected version, but the structure or the mathematical expression of a straight line does exist in nature. It's just, it's not the perfected form.
Yeah.
Is that correct?
Yeah.
great.
Thank you. That's very helpful.
Thanks, Patricia. Hannah wants to crochet a brain. Hannah, look it up. One that did that. And then I've got a question here that I don't know if it's, if I can find it. I don't know if it's actually one that you would be interested in answering or not, because it's talking also about chemistry in biology, and I'm not sure what your background in is that. I'm going to read it to you. How does math relate to stereochemistry in biology? There are infinite shapes in nature. I admire them on my hikes. Is DNA related to math and stereochemistry? And also he says, great presentation. Thank you. So I'm not sure how much you want to go into that, but reading it out.
Well, so this is what I was like putting in one of the chapters, like last chapter, where all these geometries are used and how it's in stereo. Well, okay, so I'm not like a chemist, so like, but there is a thing which you can have I forgot, like there are if you organize like a new drugs, there was a one drug, if you put it, like if you put it one way, so then that drug is very good. If you put it the other way, so then that is a poison. So like these symmetries. Yeah, so okay, so yes, well, help me. I just like lost the word of, I don't want to say the wrong thing, but that's like that's how the geometry is like really, like so connected with the chemistry. And
I think this is the case for sugar, right? If it's a right-handed sugar, it's fine. If it's a left-handed, it's poison. I learned this in a chemistry class.
And Wilbur, I'm trying to invite you to unmute and to put your camera on, but I can't because I'm not the
okay
host,
yes
so.
No, it's yes, but that's like I don't have like such a strong background in like my stepdaughter is a chemistry teacher, so she was like showing me like these examples. And actually, well, what I must say is, since I started to crochet hyperbolic planes, clearly finding a meaning for me, mathematical meaning. But then the people were jumping in because it was sort of like in a visual way showing how it connects what people are doing. And I was learning about things about these nudie branches, like biologists told me, oh, this is what we have and this is what we happen. And that's how the nudie branches made it into my book. And then there were like some physicists, like there was a one grad student, he said, oh, I had to describe like these solar winds, and she shows me a picture, and that's exactly, and she says, oh yeah, now I know what I can use. And then I think there was like a very nice is about like how leaves grow, how is the edge of a leaf. And that's like one of the ways where you can experience with kids what the curvature is. You pick up the leaf, you know, like when it's, now it's fairly light, they are already dried and, you know, like no more. But when they are just starting to fall, they look pretty flat. And then children will say, oh yeah, no, the leaf is a flat. But then you can have scissors and take off like an edge of the leaf and then trying to put it down, and you can't. And then it just like overlaps. So that means like, so, you know, there is some curvature. There is some curvature in the leaf. This was, well, Bill Thurston liked to do it. So the same thing is you can just like a peel orange, you know, like, but in a thin strip all around, and then try to flatten that one, you know, like, and that's the ways how to explain, like how to explore curvatures. And I have done it with fifth graders. That was like in Arkansas. So we were doing math teaching, like experimental project with the fifth graders, which is in a very low school. Nobody really cares. Those are some immigrant kids and nobody really cares what you do with them. And it was such a wonder. Those kids were so wonderful. They were like, because, you know, like nobody really cares. And we could go in with these crazy ideas, bring in like, you know, like a scissors and make a models. And for them, it was like a whole play with mathematics. And then everybody was shocked how well these kids did in math because we were just like playing.
Yeah.
Yeah, so yeah, that was wonderful. But when, of course, when we wanted like expand that curriculum, then like came in, oh no, it doesn't go into like, you know, like these, like the between the lines and what is prescribed to be taught to kids.
There are comments, I don't see them right now, about Steiner and I think the Waldorf schools and such, through learning through experiencing. And I certainly wish I had had more of that. Is Andrew here? Can you see him? Shall we just read his question? Is he still here, Susan?
He
may have left.
He had to leave, but I put his question to the chat, but I can read it.
Okay, sure.
Yeah, so Andrew asks, are hyperbolic surfaces necessary in living structures, given the way they build? And do they confer evolutionary advantage?
That was explanation given to me with biologists, because this is how you grow. And let's say, so the best you can see it like with a sea kelp, when you compare what kind of kelp is closer to the top of the ocean floor and which is deeper down. Deeper down kelp is more convoluted. And then one which is up on the top is like sort of like a lightly convoluted and is more flat. Because the kelp needs, in order to grow, it needs like nutrition and it needs the sunlight. If it lays on the top of ocean floors, it can be like relaxed. I will get all the light I need. Something which is down, you know, like, oh, no, I have to grab like a maximum. So that hyperbolic shapes in nature appears when you need a maximum surface area in a minimum of a volume. So this is like what we're showing, like this thing. Yeah, so, you know, like this is like a maximum surface area, you know, like in a minimum volume. Yeah, so, you know, I want to grab as much as I can.
Which there we're going again for efficiency, which is one of the first principles. Dana, will you show people the picture that you showed us before we began? Because, you know, in the body, we do have these hyperbolic.
Yes, we do have it in the body. So yes, like I'll show us a picture. And then people can make a guess.
Neil might know. Who?
Okay, well, you need to spotlight to everybody. Okay.
Whoever's the most.
I'll take a wild guess at mesentery.
No.
So yes, well, and then I bought the book. I'm not showing you like
it's a Bowman's capsule.
Yeah, the real thing, because like I bought the book because it reminded me very much of this.
And I see the book and I would love it.
This is, yeah, so this is at my biggest plane. Well, I have it at home, but it's in a storage and it's 13 pounds. I didn't bring it out. So, you know, like that, no, it's well. Yes, but then the thing which I was like showing you, and then I was just like accidentally in a store opening a book, and then like, here it is.
And
Which
Neil,
reminds
it
me
is
very much.
magnified, what, 47 times, right?
It's 47 times and large fallopian tube.
Oh,
Yeah,
I
those are
see
the fallopian
tubes. Oh,
tubes. Yeah. So yeah, and then just like, you know, having, because I don't like much of a pink color, but then seeing like this pink thing enlarged, okay, then I felt better about my big one. So yes, but it's like, so yeah, no. And then I'm told that there is also in our intestines, microflora is also like making sort of like this hyperbolic, you know, hyperbolic thing. So you just like everywhere when you want to grab maximum nutrition. So
Yeah.
yes, yeah.
Pedro says yes. Chirality is essentially handedness. You see it everywhere in the brain, in the belly.
Well,
all over the place.
brain. I was asking about the brain. You know, like because it's they say like, okay, so this looks like a brain. Which actually no, it's only the surface. The brain itself doesn't like that. I was asking neurosurgeons about it.
Okay.
But what is happening with the brain, that we are storing information in a brain. If you want to map that information, then it can be mapped on this hyperbolic plane. Because it is like sort of like if you have this, and then there are like a web search engines are being, you know, like saying no more advanced, but the very first ones definitely they started to make it on these hyperbolic models. Because for example, if you want to know how to get from this point to this point, so you know, like there is no way we even know how to go. So how do we go is we go straight down to the center and from center back. So, and that is how we are dealing with information in our brain too.
That's very interesting. I'm looking at the time. It's already 10:02. So maybe what we can do is, first of all, I think we got to all the questions. I've typed something in the chat about Mahadevan's work when he's looking at growth differential and energy minimalization and morphology, but we need to keep the ball rolling. So Graham, are you ready to do the sponsors? And while Graham is unmuting here, there's so much more we can love to be in the same. Go ahead, Graham.
Yeah, thanks, Chris. The Biotensegrity Party is an all-volunteer production of the Stephen M. Levin Biotensegrity Archive and made possible in part through the generous support of our wonderful sponsors and our volunteers. So a quick summarise here with Handspring Publishing in East Lothian, Scotland, have a wide range of authors and books suitable for the movement and manual therapy professional. They're offering a generous discount which you can to all Zoom participants, which you can see in the chat. They're also generously supported by Chris Clancy's educational organisation, Embodied Biotensegrity in Vancouver, who provide an excellent resource for those of you looking to learn more about biotensegrity. Then we have sponsorship by Artifact Pro of Madrid, Spain, where you can find these wonderfully constructed anatomical tensegrity models. Artifact Pro also offers a discount coupon to the Zoom participants. Then we have the Fascia Hub, which is a newly started up in the UK, where you can find full day talks coming up in the Saturday, 28th of November on the fascial pelvis. And there are several speakers for that, and that's a bargain. So there's a discount, I believe, in the chat for that also. So go to thefasciahub.com. And finally, Integrated Biotensegrity in Alberta, Canada, are holding a one-day course tomorrow, so you better get in quick, with Lisa Babiuk, Paul Thornley, and Rachel Tudor. So check out all our sponsors and support them. Thank you.
Thank you, Graham. And so next week here, it's either Susan or Mariana. Who would like to tell us about next week's Biotensegrity party?
Mariana, are you there?
I am. Yes, yes, very exciting. Next week, I'm going to be with Leonid Bloom and Dr. Brad Fullerton I'm hoping I'm pronouncing that properly. Yes, we're going to be talking about something that is not commonly said out there. Everybody's talking about releasing fascia, releasing, and I think we are creating more tension in something that is not really holding properly. So I think it's going to be a very interesting conversation. We have Dianes and I, we have the experience with the kids who have cerebral palsy, and Dr. Fullerton, he's doing something more into the athletic world or like patients with pain, but he's also working on the fibroblast. So I'm very excited what's gonna emerge from that conversation.
So Mariana, rather than having the harder, tighter parts release, the other view is to get the parts that maybe are too loose, not as involved, to get them shored up and stronger, which will then allow perhaps the over tight parts to release because they're trying to compensate.
Exactly.
You're all doing it, I think.
Yes. So I think it's going to be a very good one. So you're all welcome here.
Okay, thank you, Mariana. And we like to finish with a toast. Dinah, this has been a real pleasure. Will you give a toast for us, please?
Yes, well, thank you very much for inviting. And and let's toast to art, math, and biology, and to all of your interests. And so and have a wonderful weekend.
Thank you. Cheers.
Thank you, L'chaim.
Cheers. Okay, Mariana, I'm not host.